Hello and welcome back to the Quantum Ansul. In the previous video, we discussed about magnetic field lines. Now, let's solve an important assertion and reason question related to magnetic field lines. The assertion says, no two magnetic field lines are found to cross each other. This statement is true. The reason says, a compass needle cannot point towards two directions at the point of intersection of two magnetic field lines. The reason is also true. Let's understand why. Magnetic field lines represent the direction of magnetic field at different points. If two magnetic field lines crossed each other, then the point of intersection there would be two different directions of magnetic field. But a compass needle placed at a particular point can point only in one direction because it aligns itself along the magnetic field line direction. It cannot show two directions at the same time. Therefore, two magnetic field lines can never cross each other. So both assertion and reason are true and the reason correctly explain assertion. Hence, the correct answer is option number A. Now, let's solve another important question. The questions ask, which one of the following statement is not true about a bar magnet? Option A says, a bar magnet sets itself in the north-south direction when suspended freely. This is true because a freely suspended magnet always aligns itself with Earth magnetic field. Option B says, a bar magnet has attractive power for iron filings. This is also true because a magnet attracts magnetic material like iron, especially near its poles. Option C says, a bar magnet produces magnetic field lines. This is true because every magnet creates a magnetic field around it. Option D says, the direction of magnetic field lines inside a bar magnet is from North Pole to South Pole. This statement is false. Remember, outside the magnetic field lines go from north to south, but inside the magnet they go from south to north. Therefore, the statement which is not true about a bar magnet is option D. Now, let's understand the magnitude or strength of a magnetic field. The strength of a magnetic field is shown by the number of magnetic field lines around a magnet. When the magnetic field lines are closer together or more crowded, it means the magnetic field is stronger. When the field lines are far apart or less crowded, the magnetic field is weaker. In a bar magnet, the magnetic field is strongest near the poles because the field lines are closest there. As we move away from the poles, the field lines spread out and the magnetic field becomes weak. So remember, more crowded field lines mean a stronger magnetic field and fewer field lines mean a weaker magnetic field. Now, let's learn about uniform and non-uniform magnetic field. A uniform magnetic field is a field in which the strength and direction are the same at every point. In a uniform field, magnetic field lines are parallel and equally spaced from each other. For example, when field lines are straight, parallel and the equal distance, the magnetic field is uniform. On the other hand, a non-uniform magnetic field has different strength at different places. In this type of field lines are not parallel and the distance between them is not equal. Near a magnet, the field is usually non-uniform because strength changes from place to place. So, uniform field means same everywhere, while non-uniform field means different at different points. Now, let's see magnetic field line due to two bar magnets. When unlike poles, that means north and south poles, are brought close together, the field lines join between them. this shown attraction between opposite poles, the field line become dense in the space between the magnets, which means the magnetic field is strong. But when like poles such as north-north or south-south are brought closer, the field lines move away from each other. This shows repulsion between similar poles. So, opposite poles attract each other and same poles repel each other. In this activity, in this activity 12.2, we will observe magnetic field lines using iron filings. First, place a bar magnet on a white paper and sprinkle iron filings around it. Now, gently tap the paper. The iron filings arrange themselves in a pattern around the magnet. This pattern represented magnetic field lines. We observe that the iron filings form curved lines around the magnet. The filings are more crowded near the poles, showing that the magnetic field is stronger at the poles. Therefore, iron filings help us to see the shape and strength of magnetic field around a magnet.